Hello, I'm Dr. Kathleen Schmidt from Lawrence Livermore National Laboratory. Welcome to the Data Science Institute's virtual seminar series. With Lawrence Livermore being home to many challenging data sets, as well as some of the world's most advanced supercomputers, data science has become an essential discipline in the lab's key program areas. The DSI acts as a central hub for the lab's data science activities by fostering collaborations, promoting research, and engaging in outreach activities. Our DSI staff work in a variety of areas, including artificial intelligence, big data analytics, computer vision, machine learning, predictive modeling, statistical inference, and uncertainty quantification. The DSI hosts events like this seminar series to introduce new ideas and potential collaborators to the lab. We invite speakers from other institutions, both from the Bay Area and beyond, to share their innovative projects, approaches, and ideas with our data science community. We're pleased now to include a wider audience beyond the lab to engage with us through this series. You can read about past speakers on our website, data-science.llnl.gov, or email us at datascience@llnl.gov. Thank you, and enjoy the seminar. It's my pleasure to introduce Dr. Lizhen Li. She is an associate professor at the Department of Applied and Computational Mathematics and Statistics at Notre Dame. Her research interests include Bayesian non-parametric models, geometric deep learning, and statistical network analysis. And I'll turn it over to her to tell us about her work in Variational Bayes.
Thank you, Katie. I'm going to make this full screen. Okay, can you guys see my slides? All right, so thank you for coming to my talk. So I'm going to talk about Variational Bayes and adaptive Variational Bayes. And now, of course, this notion of adaptivity will be clearly related. And I want to thank Katie for inviting me to speak at your seminar series. And I know Katie mentioned about my talk at GSM last year. I was talking about scalable Markov chain Monte Carlo, so MCMC methods, where David Blind was talking about variational inference. And today I'm actually going to speak kind of his topic about variational inference, but more focused on the methodological and the theoretical aspects of Variational Bayes. And in particular, the theoretical development of Variational Bayes, pretty new, pretty cutting edge, I would say. It's sort of emerging work. So although Variational Bayes has been very popular, as David Blind has talked about in his talk last year, GSM or introductory lectures, but the theoretical aspects were just starting to emerge. So this is a joint work with my postdoc, Yisang Oh, and he's also an expert in addition to being an expert in Bayesian non-parametric theory, he's also an expert in deep learning theory. So if you're interested in development of statistical aspects of deep neural network models, you probably will came across his name here and there. So, okay. So, all right, so here's the, okay, put it my screen. Here's a brief sort of outline of my talk. So I was, as Katie was mentioning in the email that I should go start with something more sort of a simple introduction on Bayesian inference and also Variational Bayes before we get to the core stuff about our work, which is called adaptive Variational Bayes, adaptive Variational inference. And then I'll talk about the posterior contraction rates and the model selection consistency of the adaptive Variational Bayes. So the theory relate to, so this is sounds pretty, if you are not familiar with the Bayesian non-parametric theory, so those words such as contraction rates and model selection consistency might not look so familiar to you, but I'll explain the general idea for the theoretical. I will give you a very brief sort of high-level overview of what type of theory Bayesian is interested in, right? So the frequency theory, for the frequency theory, which is sort of tied to the classical statistical theory, I think that most of you are very familiar with, right? Because that's how we were trained when we were taking like statistics courses. You have like, say, central limit theorems, right? You have a convergence in probability, convergence in like convergence in distribution, which is of course like related to central limit theorem, convergence in probability or consistency, or convergence in distribution, which, like I said, is central limit theorem. Those type of frequency theory are sort of, I think, more familiar to most of you. But Bayesian theory, there's also sort of Bayesian theory. So it's Bayesian, the so-called Bayesian asymptotics, which is also sort of has its own sort of field, like starting at the beginning of the 2000s. So there's this development of the Bayesian theory, in particular Bayesian non-parametric theory, which is kind of relevant to our talk here. So I'll give you a lot of stuff very technical, but I'll give you a high-level overview of that. So just so you know, next time you see the things like posterior contraction rates or model selection consistency, you know, so you will not be a sort of a fresh new stranger thing to you. Okay, now I'll also illustrate with some examples and applications. Okay, so let's first start with Bayesian, a very brief review of Bayesian models, right? So Bayesian approach sort of versus the frequentist approach that most people are very familiar with. Bayesian approaches are very general, right? So it's like they're pretty general. They're general methods for modeling complex data, in particular big data. So the reason is that because it provides provides this full probability measure, the so-called posterior distribution on the space of parameter of interest. It's very general, and it has the ability of measuring uncertainty because you have the posterior distribution of what you're interested in estimating, right? So with that distribution, you can do a lot of things with that, right? You can get a samples from that distribution, take the average to get a point estimator, or you can construct a credible interval, right, based on this posterior distribution. So Bayesian methods has this appealing feature of being able to measure the uncertainty of the model, of the estimate. Okay, so very simple thing. It's general setup. If you have a parameter theta, which could be anything you're interested in estimating, okay, so then you start with the pi distribution pi of theta. Then L stands for the likelihood of the data, and the posterior distribution is given by the same pi, or you can use a p of theta given the data. It's just given by the simple Bayes theorem. Okay, you apply in the numerator the pi distribution multiplied by the likelihood, and the denominator is just this marginal likelihood with respect to pi. So the denominator is in a complex model in general uncheckable, right? You want to integrate this likelihood with respect to pi, and that's the typical intractable normalization constant. So that's where the MCMC methods come in, right? You can MCMC methods allow you to sample from this posterior distribution without having to evaluate this denominator. Okay. So like I said, Bayesians are sort of universal methods. In a sense, they are very general. So this parameter theta can be anything interested, anything you want to estimate. Okay, it could be mean. It could be the mean parameter of the Gaussian distribution. It could be the variance. It could be the sparsity of a model, right? Suppose you have a high-dimensional linear model where typically use Lasso or there's the frequentist high-dimensional regularizing method. You have sparsity of the model. You can impose the sparsity on the model, express the sparsity through a pi. It could be a partition parameter. For example, you have a network model. You are interested in community detection by dividing the nodes into partition. So that itself could be a parameter. And we actually are going to talk about that today, about this stochastic block model, where you actually can infer the community structure and also as well as the link probability between nodes or things like that. And the parameter could be a function, regression function, like Gaussian process model prior. And the parameter could be also a density or probability measure itself. Okay, just very quick overview of Bayesian model. So the general idea of Bayesian modeling is that you are going to sort of impose a distribution which is called a prior for your parameter of interest. Okay, that prior is going to meet the likelihood, and then when the prior updates with the likelihood, which will yield this object called a posterior distribution. Okay, posterior distribution is again a distribution with the parameter of your interest. That's the ultimate object you're going to be using for statistical inference. Okay, so if you have the posterior distribution of the parameter of interest, you've got this very rich information about the parameter, right? You can sample from it, typically using MCMC method. With those MCMC samples from your posterior distribution, you can take the average, you can construct credible interval, as I mentioned, right? So that's really the general philosophy of Bayesian inference is that you get this posterior distribution of what you want to estimate. And that posterior distribution provides a very rich information about the parameter. Okay, now, however, there are some sort of computation challenges for Bayesian modeling, in particular with Bayes data. If your sample size is big, and the key challenges come in sampling and posterior distribution, as I said. And so the Markov chain Monte Carlo methods, MCMC methods, I'm sure this is probably not a new thing to, Lawrence lab, given you guys are so good at computation and have a lot of expertise and computation power. And MCMC methods are typically used for sampling the posterior distribution. For example, you can have a Gibbs sampler for sampling multivariate parameters, right? You can have Mitchell histine, and you can also have, typically you need to run a Mitchell histine within a Gibbs sampler or things like that, right? So Markov chain Monte Carlo methods are the popular method, in general, the general methods that you almost most of the time have to use the MCMC method for sampling posterior distribution, unless your posterior distribution is in a closed checkable form, which is very rare, right? Unless in very simple models. Like I said, for the fully MCMC method for sampling posterior distribution can face sort of a lot of computation challenges, right? Especially for large and high dimension models, or models that requires sort of your Markov chain Monte Carlo to move between models of different dimensions, right? If you probably have heard about those models like the MCMC algorithms, such as reverse jumping algorithm. Basically, if you have models of different dimensions, this is going to happen in our case in this talk. I will show you this model selection problem. So if your MCMC needs to sort of travel between models, right? Transverse between models of different dimensions. Then in general, its computation efficiency is not that high. So you face all kinds of challenges doing that. Now you have to have very clever proposal distribution in moving around this union of a parameter space of different dimensions, essentially. Okay. Anyway, so that's MCMC methods are not going to be the focus of our talk today, but I just want to give you some general ideas why MCMC methods can face the computation challenges. Okay, of course, if you want to stick to MCMC methods, there are certain things you can do to speed things up. For example, you can do divide and conquer methods or things like that. That's what I talked about last year in the scalable MCMC lectures at the JSM. But today, we are going to sort of look at the posterior approximation method. And a number of such methods are available. So you have expectation, EP, expectation propagation, you have Laplace approximation of the posterior distribution, or you can have variational approximations. And the variation methods are going to be our focus today, and they are most popular one, as I said in this bullet that variation methods are almost most popular model and successful in practice. And David Blinds give this very great talk last year. Like he gives lots of examples in terms of how you can make variational work, all kinds of scenario. And there's also a recent thread on scalable algorithms for sort of very huge streaming data. So variation Bayes in general, computation is very powerful, and they are very, how to say, they can scale to very big data sets, even with streaming data nowadays, as I said, some recent development. Okay, so the variation approaches provide approximation to the full posterior distribution. Okay, and like I said, there's emergence of a recent theory on how good the approximation is. So they tell you have this variation of posterior, and there's theory quantify how good the variation posterior is. For example, the variation posterior distribution is going to concentrate on the true parameter of interest, right? So that would be what the people in Bayesian theory are interested in. You have this posterior distribution. Ideally, you want your posterior distribution to concentrate around the right place, right? The true data generating parameter. Okay, so we'll talk a little bit more about that. We'll talk more about that, about the theory. Okay, of course, there's this one potential drawback is that sometimes you can underestimate the posterior variance. Okay, so what we can do, so first I would like to provide a very simple introduction on the Variational Bayes framework. Okay, just sort of give you guys a review of what the Variational Bayes framework is. Then before go to our adaptive variational framework. Okay, so that's actually a new methodology I would like to introduce to you. It potentially could be useful in your, if you are using variational Bayes for any of your problem. So what we propose here in this talk might be useful to you actually in terms of so I would say in terms of providing alternative methods of doing variational inference. Okay, so what is variational Bayes, right? So variation Bayes provides approximation to the posterior distribution of the unknown parameter, right? With members in the variational class. Okay, so let's stop here for a second. So you have this two posterior distribution in a standard Bayesian inference framework. Right now, you are going to approximate that posterior distribution with some simpler variation family. Say, I'm just going to approximate my posterior distribution with a Gaussian distribution, right? What I need to determine will be what is the mean and variance of my Gaussian distribution in this variation family or variation class. I'm restricting my variation class to be a Gaussian class, for example. Then I'm going to find a member in this Gaussian class which provides an approximation to my, as closest approximation to my posterior distribution. Because what do I mean by closest approximation? How do I define that, right? So that's in terms of Kullback-Leibler divergence, of course. So okay, you get the general idea, right? So variation Bayes basically picks some member in variation class to approximate the posterior distribution. The idea is very simple. Because if you pick a very simple, if you pick a simpler variation class, then maybe inference will be a lot easier, right? Instead of sampling MCMC, all you have to do is just use a one Gaussian distribution to approximate this this posterior distribution. Okay, so more specifically, like I said, rather than using using MCMC sampling, the main idea behind variation inference just using optimization. When I say providing this closest approximation, in general, you just need to minimize the Kullback-Leibler divergence. That's why we say in variation inference, there's this optimization thing involved here. So first, we're going to provide a family of variation family in our notations Vn, and we can assume the parameters use z. The reason I use z is theta here because the use latent variable z seems to be the most popular one they use in like Dave's paper and other people. So I just I introduce z to you. Okay, here's a rigorous definition, simple one, the below one. So Q star z. This is your variational approximation of your posterior distribution. Okay, so this Q star z is the member Q in the variation family, which minimizes Kullback-Leibler divergence between any Gaussian family Q of z with your posterior distribution pi of z given x just data. Okay, just think of it that way. Okay, does it make sense? And so that's as simple as that. Okay, the concept is very simple. You find a member Q in the variation family and the Kullback, and you want to find a Q such that the KL divergence between Q and the posterior distribution is minimized. That's it. Okay, so the KL divergence is sort of some measurements of information loss, right? It's closely related to entropy, things like that. So, okay, and this Q star is this optimized member. That's why we say we use the optimization instead of MCMC. We use the optimization. When we say optimization, we really meant this minimization of the KL divergence. Okay, I hope this gives everybody a sort of a quick review of what the reminder of what the variation Bayes is. Okay, so there's one more slide. So just quick reviewing this definition of the okay. So in the next slides, I just give you this quick reminder of this evidence lower bound. Okay, so if you write this posterior distribution, I switch back to P, so it will be easy for you to see the conditional distribution. Okay, so the posterior distribution of z given s, if you write given x, if you write in this form of a joint distribution divided by the marginal, and then you put that into the, I should use T, my notation is not very clear. So the KL divergence between Q and P, and then you just plug that in, right? So it's by simple definition of KL divergence, and then you get this second line. just a little bit algebra here, okay? And this second term is going to be just log p of x, because q is the distribution of z. You're summing all the possible z's, it's going to be 1. So it's log p of x. So we're going to get this. So you have the Kullback-Leibler divergence between, okay, I'm going to go back to previous slide. Yeah, so the Kullback-Leibler divergence between q, which is your variation family, p is your posterior distribution, that's given by form like this. Take a look, okay? So this term on the right, I don't know whether you can see my highlighted arrow now. So this log of px does not depend on z, right? So only this first term is dependent on z. And this is the KL divergence between that. Okay, let's take a look at the next slide. So this first line is exactly repeating the previous line in a previous slide. So the KL divergence between q and p is given by this expectation of the q with respect to q of log of qz minus log of p of zx plus log of p of x, right? Now if you move this term to the left, okay, and the log of p of x is given by what? So log likelihood is given by your KL divergence minus this highlighted area. We're going to call this L over Q. Okay, take a look. Okay, so you know the KL divergence is always positive, right? This is your sort of your evidence of your data, right? Log likelihood. And so L over Q, which is given by this term, expectation of a log of Q minus log of P of Zx with respect to Q. That actually is called the evidence lower bound, because that provides a lower bound of your evidence of your data log of P of X, right? Because this is always KL divergence is always non-zero, okay? All right, so as you can see, like I said, log of P of X does not depend on Q. So your minimization is over Q, right? So minimize the KL divergence in some senses, so you want to maximize this effective evidence lower bound, right? So as I put here. So maximize the LQ is equivalent to minimize the Kullback-Leibler divergence. Just simple algebra, oh, excuse me, oh, I had this. The simple algebra, it shows that the minimization KL divergence is maximize the L over Q. So this evidence lower bound. Here was my slide. Here. Okay. Okay, very good. So then okay, and sometimes if you have good choice with Q, this evidence low bound actually becomes trackable to compute and maximize. So this is LQ thing. So remember. So we will revisit this again under our framework. Okay, so the evidence low bound is kind of important objects, and so I want to provide a quick review on that. Okay, so like I said, now we have both analytical approximation of the posterior distribution P of Z given X from given a family, given member from the variation family. We also get lower bound L over Q for the log likelihood, so or for the evidence of log likelihood. Okay, and this lower bound, like I said, is called evidence lower bound. And sometimes you see it's denoted as ELBO. Okay, so it's almost inevitable you will see whenever people talk about variation inference or provide some overview of variation inference, you probably will see the ELBO. Okay. All right. So so this is probably my last slide about sort of quick review about variation inference. Anyway, you just keep this general idea what variation inference in mind, and this simple algebra allows us instead of directly. So really, I want to point out, I'm trying to mention to you is that a lot of time instead of directly minimize that, because you need to find a Q over the variation family that minimize the KL divergence. So instead of minimize the KL divergence, the point I'm trying to make here is that a lot of time you just need to maximize this evidence lower bound. Okay, so if you look at here, right? All you have to just log Q of Z and log the joint likelihood of Z and X, and you just need to maximize the expectation of that with respect to Q. Okay, so sometimes I will show you this. You minimize the negative of it, right? So you can call this the variation objective function. Okay, so that's we're going to see this again in our adaptive variational framework. Okay, so I've almost spent like 20-some minutes talking about. I hope that's okay. So I'm going to speed up a little bit so we can get to the core stuff. Okay, now what we can do. Really, the key thing I'm going to send into you today in the talk is this adaptive variation Bayes framework. Okay, so this is a new framework we propose. adaptive variation Bayes. So which is going to lead to the adaptive posterior contraction rates and the model selection consistency. So those two things you might not be familiar with yet, but this notion of adaptive means I don't have to have knowledge of what the true model is, and I can still get a sort of a optimal contraction rate, and I can still select the true model. Okay, so for this adaptivity could be adaptive to the smoothness of your model. So I don't know, when you perform regression analysis, right, you typically need to assume you know what the smoothness of your regression function, or it could be the sparsity of your model, right? So adaptive means our results stand without the knowledge of all those, like smoothness of the model, with the sparsity of a deep neural network, or number of components in the mixture model, or things like this notion of adaptive. Okay, it works to a broad class of learning problem, in particular ones that involve model selection. Okay, like some example I said here is mixture model, deep neural network model, stochastic block model, factor models. So all of those models, there is this model selection component here. Okay, in the mixture model, you have to select how many components, the mixture components. In the deep neural network, typically you have to select the sparsity, the number of neurons, or things like that. And the stochastic block model is the same thing. Okay, so here comes the key idea for that. So the key idea is that to first obtain the individual variation posterior for each of the individual model. Okay, then which are in some sense aggregated to obtain this final variation of posterior distribution over the whole model class. So like I said, you have model selection, right? So you say, suppose you have like a mixture model, you have five mixing components. So your model selection will involve components 1, 2, 3, 4, and 5, right? You can get a variation of posterior for each of the sub-model with 1 component, 2 components, 3 components, 4 components, and 5 components. In the end, you're going to aggregate those variation of posterior in those individual variation posterior to obtain this final variation of posterior distribution. Okay, and I'm going to show you with some of the examples. Okay, so first let me introduce some of the notations, which is a little bit of this talk is going to involve a lot of notation, but anyway, so most of it you just need to get the general idea of it. So you have MN, just sort of countable model indices. I say MN could be like the number of components in your, or number of cluster, or the number of neurons in your model, okay, with the sparsity level. And so we have this M and M is a collection of probability distribution indexed by for each of the model, individual models, N and M, okay? N is sample size, M is sort of the number of so sort of M indices the model. Okay, so we have this T map, which is kind of important. This T map is sort of natural parameterization of the model. Okay, so that's really it. So keep in mind is N M. Let's say okay, M just indexes the model selection components, like say how many cluster, how many number of components a mixture model has, or things like that. Okay, and this map Tn is called the natural parameterization map. Okay, I'll show you this a few examples of Tn, which is very, very natural. Okay, and those theta, the parameter n and the mn is sort of the whole parameter space, which is simply the union of theta, and m, where m runs through all the model indices, right? It's just a union of a mixture model with all the possible number of components, for example, from 1 to 5. Okay, so the small m would run through from 1 to 5, and the theta and m would be like just the parameters from the parameter space of each individual model. Okay, so I know the notation looks a little bit some sort of technical notations, but just we really need them in order to be able to present all the results and sort of rigorously define everything. Okay. So now I'll give you some simple examples about this. Okay, so it's one of the examples is factor model, high dimensional factor model. Okay, so it's like really just you have a sample y1, yn of high dimensional Gaussian distribution, multivariate Gaussian with covariance matrix sigma. And in the high dimensional factor model, they assume the sigma really just so your y can be really expressed by some by m factors. That's really the idea. Okay, so the infected model, you assume your heterogeneity of your data can be expressed through the small number of factors, m number factor, and your covariance metric can be decomposed as theta times theta transpose, and this theta is your factor loading matrix. Okay, so in this case, your m is just really number of factors. You know what I mean? When you have different number of factors, and you basically have a model selection problem, right? So your parameter space are disjoint. So I'll show you here. So basically this is your model, right? So your m is smaller than the dimension of your factor dn is smaller than 1, and all those parameter space are disjoint. Okay, so factor model requires factor selection. How many factor the so-called factor dimensionality, or the number of factors. You know, depending on the number of factor, so your model would have basically your model runs from disjoint spaces depending on how many factors you have. Of course, if you assume that you know the number of factors, then the problem is pretty easy, right? Then there's no model selection. You don't have to select the factor dimensionality with the number of factors. Okay, this is one example showing you that. So our adaptive variation framework applies to almost most of the model selection problems. Okay, and of course, even you don't have model selection component, the methods also applies. Of course, just a special case, right? And factor models is one of the very, very simple and important example. Factor models nowadays has sort of they're very popular in finance, in modeling the high-dimensional finance data or time series data, so things like that. Okay, and also another example is finite mixture model. Okay, so finite mixture model basically says for example, your data can be modeled linear combination of 5 Gaussian components with different locations, right? Say I have 2 Gaussians, I take 1/2, 1/2. That will be your Gaussian location mixture model. So linear combination of two Gaussian components. Okay, and in this case, your parameter, okay, although this looks complicated, but actually the mixing distribution T here is given by omega k is just the weights, the mixing weight, and the phi is just your Gaussian distribution, and your centers around the mu of k. Mu k will be your the center of your each mixing component. Okay, this T is actually called the natural parameter here is the so-called mixing distribution. Okay, and m is your number of component, right? So for example, we assume that our data are generated from some mixture model, but we don't know how many mixing components are there, right? So it could be, we will say, we assume it's less than 5. So it could be 1, could be 2, could be 3, could be 4, could be 5. So m runs from 1 to 5. So that is a model selection component here. And then your parameter space is just indexed by this mixing distribution, or the mixing weights, and or the mixing locations. And those parameter spaces are also disjoint, right? You have 1 component model and 2 component model. They're disjoint, right? One's not basically one model consists of all the distribution with one mixing components. The other one consists of all the distribution of 2 mixing components. Those parameter spaces are disjoint. Okay, another example I want to show you the stochastic block model. Okay, the stochastic block model is very simple. Okay, so I know again a lot of notation. I'll just explain the general idea to you. You have a network. Okay, you assume your network, the Yij's, they're binary. It's like whether you and I are friends on Facebook or not. Okay, they follows from some link probability matrix, which by some Bernoulli distribution. Okay, with some Bernoulli distribution with some link probability omega ij. So the link probability actually uniquely determines by which class you are in. So this U, Z, and UJ. Z would depends on which, this notation with ZI transpose U, ZJ basically tells you that. So if you and I are in the same cluster, the link probability between you and me is the same between the link probability anybody in the same class with us. So the stochastic block model basically means your link probability, where the probability of any 2 nodes being friends or not is really uniquely determined by which cluster you are in. So, and those U will be the block matrix. Okay, so this is M by M. If there are M clusters, okay, so U is those block matrix. So your link prob matrix omega is uniquely determined by your block matrix U. And this is just the membership of your node, which class you are in. Okay, I hope that they give you an idea what a stochastic block model is. Really, the property of your network is really unique by the cluster, which means everybody in the same class behaves almost sort of stochastic equivalent, right? Suppose you and I and somebody else are in the same class, which means the probability, link probability between any of us is constant because we're in the same cluster. And the link probability between me and somebody else from another cluster is the same as the link probability between me and somebody else who are in the same cluster with that guy, with that person. You know what I mean? Okay. So this is also a model selection problem in the sense you have to select the number of clusters there, right? M. And those parameter spaces are also destroyed. Okay. And also there are many other examples, right? Like you can also have a sparse linear regression. You also have to select the sparsity of your model. You want to know which of the linear coefficients are 0 or non-zero. You know what I mean? So that's also a model selection problem. And also in the deep neural network model, which are very popular nowadays, right? You have to select the number of neurons and the sparsity of neuron, which neuron non-zero, things like that. So just they're almost universal problems, right? They're ubiquitous everywhere in the learning in our modern data science. So okay, now here I'll introduce our framework. So like I said, okay, let's pause here for a second. Look at this notation here. So we have the parameter space, which is written as the union of the individual parameter space, depending on how many components, how many clusters, and how many factors you have, right? Then the prior distribution is going to be, we're just going to put a linear combination, right? So the prior, not linear, I know using linear combination is not very most precise term, but you see my idea, right? So you're going to pi n, the prior distribution is expressed by this sort of, in some sense, kind of mixture, right? Alpha n m times pi n m. Pi n m is the prior distribution for each individual model, okay? And you can interpret alpha n m as pi probability of each model, each individual model. That's what my already says here, right? The prior probability of each individual model. And then with this prior distribution, you're going to get a posterior distribution, the overall posterior distribution, right? By the standard Bayes theorem. Okay, that's it. The QN is just a likelihood function. So nothing fancy in this slide. Okay, we just introduce a prior, which is a mixture of the distribution of each of the individual models. Suppose we have 5 components, then that would be 5 different prior, right? With prior on different on models of different parameter space. One cluster, one mixing components, 2 mixing components, 3 mixing, 3, 4, 5. Okay, and the prior is linear combination of that. Okay, very good. So what are we going to do? We are going to provide a variational approximation of this posterior distribution. Okay, and of course, if you want to provide a variational approximation, you need to know what your variation, define what your variation family is. Our variation family also of the form of these individual models. Okay, it's a mixture of individual models. So this V of small nm, this model, so would be, you can think of a variation family for individual model. Okay, so Vn will be the variation family, which is linear combination of variation families for individual model. That's it. Okay, does it make sense? So we are going to pick a member in this family to approximate the posterior distribution here. Look at the equation 3 here. Pi n given yn, that's the overall posterior distribution. And this Vn is our variation family. We want to minimize the KL divergence. Okay, I hope the idea is simple enough, right? So the general picture is that we have this model selection problem, right? So we're going to divide the whole parameter space into union of models of a different dimension. Okay, so our prior distribution is a linear combination of priors on each of the individual model space. Okay, our variation family is the same thing. For each individual model, we can provide variational family for that, right? Then the variation family for our whole parameter space is given by this, our Vn here. The gamma AM and the VNM. So linear combination, the individual variation family. Okay? So, okay, now let's keep going. Now let's see what is our this Vn hat here. I mean, I actually don't know how to say this. I call it Vn hat. Yisan the one who defined this notation. So I think I should have asked him. So I'm going to call this V hat n. So you know, it's probably it's not correct to say it's Vn, but you know that's just our variational approximation. Okay. Okay. Now this slide is exactly repeating the effective low bound. Okay. Did you see that? So we're going to define this variation object function, which is negative log likelihood, right? Plus the KL divergence. Do you guys recall what the thing is? Right. This is exactly what I introduced to you in the effective lower bound. Okay. So KL divergence so negative that should be the effective lower bound. Sorry. Okay. So like I said, the reason I introduced to you about this effective evidence lower bound is that typically when you perform inference, perform real computation, you actually optimize this. You either maximize the effect. So negative this epsilon term is called the evidence lower bound, as I introduced to you, right? And so you either maximize the evidence lower bound or minimize this term, this epsilon term, because like I said, negative epsilon is the evidence lower bound. So okay, so and then this is we're going to call this the variational objective function. Okay. Okay, as I'm going to repeat in this, the negative, this definition, variational object function is called the evidence lower bound, as I introduced to you earlier, which the name is after property because it provides the lower bound, right? Did you see that? Does this look familiar to you? It's a negative epsilon, which is the negative of our variational object function, is really just the effective evidence lower bound. Okay, so evidence lower bound does not just provide the conceptual lower bound of your evidence, right? Log likelihood. It also provides you another object, as we call it here, the negative of it. We're going to call that the variational object function, something a little bit more convenient for you to minimize. Okay. All right, now let's take a look. We're going to provide you a general and efficient scheme for computation. Okay, sounds like this minimization has to be done with the whole parameter space, right? Theta mn. So, and which is very big. Sounds like it very computation daunting because you have to minimize this over the huge parameter space, which is given by the union of models of different dimension, varying dimensions. So, but we're going to show you a theorem which tells you that this solution actually turns out to be very simple. It only requires the minimization of the individual models. Okay. So I'm going to show you the theorem here. This theorem, basically the equation 5 is really the equation 5 is really the space out the results, right? It tells you this variational posterior V and hat is really just linear combination of the variational approximation of each individual model. Does it make sense to you? Equation 5. That's really what it is. Okay. So V and hat turns out to be the weighted of individual variation posterior. So that's why at the beginning of slides I told you you can interpret our methodology such that you obtain a variation approximation for individual models, right? Then you aggregate that by this weighted sum. Okay, and I will give you explicit what, and this V and M hat is really a variation approximation of each individual posterior distribution. And the IM hat is just, of course, the normalization, the weights for that. Okay, so I'll show you, I'll put in an algorithm environment. You can see this. Okay, so it's pretty simple. So you import a sample of data and you apply distribution for your individual models. I mean, for the whole model, but which is sort of weighted, a mixture of a prior distribution for the individual models. Okay, and you also supply a variational family, Vn, which is also can be given as a linear combination of a variational family for individual models. Okay, then what you do is very simple, right? for all the models, M, small m is like the dimension of a model runs through the model indices, all the model indices, and you compute this variational approximation of the individual models. Okay, then you compute the weights of each individual models, posterior variational weights. Then the variational approximation for the whole model is defined by this. Okay, so I want to, how do I explain this? I want to sort of introduce to you guys in the sense that you can think of this sort of as models. Are you guys familiar with model averaging, right? So it was very popular, right? Still popular, of course. You can think of this some kind of sort of analogy of model averaging in some sense. We have individual, but of course in this case it's not like, okay, you can draw some analogy with that, but it's not the same thing, of course, because in our case we have those individual models for different because the supported space of each individual model is different. Okay. Any questions about this variational framework and the adaptive variational framework? So it's been a lot of I've been showing a lot of notations, but it's just really I couldn't find any other ways of showing them without sort of properly introduce all the notations. But I hope the idea was hope for this general picture, this general methodology is familiar to you, right? So this basically provides you a way of doing like simple variation inference in terms of scale to the big models, right? Especially how does that make, let's put it this way, make Bayesian inference more scalable for model selection problems, right? Typically, if your model involves model selection, then it's in general you're trouble, right? You have to search what the dimension of the model. You have to search the number of factors, the number of components, the number of neurons, things like or sparse state of the model. In general, it's pretty difficult. Okay, and our solution basically gives to you, is that you just provide a variation approximation for individual model, then you aggregate them together. It turns out that is just the variation approximation to your whole parameter space with the variation family Vn, with the variation family Vn. Okay, I have to go back. So Vn, which is given by the sort of weighted average of variation family for individual model. Okay, so that's the methodology part, and then we can talk about the variational, the posterior model probability. Now you have this variational posterior, right, which is a distribution, okay, which is the approximation of your regular posterior distribution. So I want to provide you results to tell you what is the variational model probability and the true regular posterior model probability. Okay, to see how close they are. So take a look here. So for the regular posterior distribution is given by this. Okay, the regular posterior distribution in equation 8. Just linear combination of posterior distribution of individual model, and those alpha and hat is just really the posterior probability of that particular model, right? So, okay, so we want to know the relationship of alpha and m hat with the variational posterior model probability. Because think about that, your variation posterior distribution is technical distribution, you know what I mean, right? You want to know what is that posterior model probability, like what's the posterior probability of each individual model. Okay, let's see. Now, okay, so then this just show you what alpha and m hat is. It's really just sort of a normalization of your posterior distribution integrated with respect to the individual model. Okay, so I will show you the results. Okay, take a look. So this proposition basically tells you the L2 difference between the posterior model probability of the variational posterior model probability. This gamma and m hat is the posterior model probability for each of the variational approximation. And the alpha hat and m is the regular posterior model probability. Okay, it turns out the difference, L2 difference of the two of them is bounded above by the KL divergence of the variation posterior distribution and the regular posterior distribution. Okay, so this is great. This tells you that this proposition tells you if your variational posterior distribution provides a good approximation of your regular posterior distribution, then their corresponding posterior model probability whether it's coming from the true model, whether it's coming from the regular posterior distribution or coming from the variational posterior distribution, they will be very, very close. So they are bounded by the K divergence between them, which is nice, right? Okay, then the next what I'm going to do would be talk about the theoretical results of this adaptive variational Bayes, adaptive concentration rates. Okay, so before I start, I want to give you a very quick overview about what is the posterior contraction rates. Okay, so what Bayesians are interesting in theory. Okay, what type of theory Bayesians are interesting? Typical means you have this posterior distribution. Okay, you're gonna look at the true neighborhood of your true parameter. Okay, you're gonna say over a certain radius of your true neighborhood, your posterior distribution is gonna be concentrated of that. The posterior converges to 1 over the neighborhood of a true parameter. Okay, and this radius is called the so-called posterior contraction rate. So of course, because if the radius, the smaller the radius is, the more concentrated results are, right? That means your posterior distribution is concentrated around that very tight neighborhood of your truth. I should have a slide just to introduce this notion of posterior contraction rates. Okay, so that's the idea. Okay, so you look at your posterior, the theory of Bayesian symptotics talks about how concentrated your posterior distribution is around the neighborhood of the truth. And that's measured by the radius of the neighborhood. The smaller the radius is, the better. That means your posterior distribution is more concentrated around the truth. Okay, so I'm going to first provide the results on the individual posterior contraction rates of individual models. Okay, there we go. So this is really the posterior distribution, the variation posterior distribution. Lambda star is your true parameter. Oh, okay, there's some typo here. I'm just meant to define the distance between them, okay, the neighborhood of them. And the radius is of eta nm plus cm. I know I did not introduce the eta and the cm because there are like 3-4 assumptions I need to impose, so I did not go into detail. I will not go into detail about this. But this, I know that this looks very, very mathematical. This small o, okay, also some typo. So basically goes to, so which means, let's stare at this equation for a second. That means the variation of posterior probability outside the neighborhood of lambda star, and you take a look of radius eta nm plus cm or goes to 0. It should be small o over 1. Sorry, this I'm missing small o here. So this eta nm plus cm is the so-called posterior contraction rates. Okay, so just so you know that the posterior contraction rate is really measured by the radius, right? So this basically says the variation posterior probability outside this neighborhood of this radius is going to be 1, small over 1, with 0, sorry, vanishes. That means all the posterior mass concentrated around the true neighborhood, okay? All right, now this basically tells you the posterior contraction rates given by these two terms, eta nm plus cm, specifically what they are depends on your specific model. Okay, and I will explain to you, this is a sum of approximation and estimation error of those. So approximation error, that's estimation error. Okay, so I'm going to skip this one here and then go to, I'm almost run out of time. So then I'm going to show you the results here. So this result basically tells you the small o, sorry, again small o, there's some issue with o of 1. Leader over 1 which means it goes to 0. Leader o over 1. I'll fix that. This basically tells you the posterior contraction rates is about epsilon n. Okay, and okay, so I'm going to show you the model selection consistency. Basically, I will tell you that our adaptive variation posterior distribution is guaranteed to choose the true model. That's all I'm going to show you. Okay. So if mn star is the true model index, then we'll tell you we will be able to choose the mn star, the true model. I'll show you the results. Okay. So this one basically says no overestimation, which means our variation posterior distribution does not concentrate over the models which are of larger size of M n star. Okay, this is like M is over M n star. M n star is true model index. This result tells you our model has no overestimation. Again, this should be small over 1, which probably goes to 0. Okay. Okay. Then this slide tells you there's also no underestimation. Okay, let's take a look at the results here. Okay, no underestimation. That means the posterior probability. Oh, here we finally I have this little O here. So that means the posterior probability, our variational posterior distribution does not concentrate over model of smaller than M star. And with those two theorems, we're able to show that our variation posterior distribution concentrated around the model of exacted M n star, the true model index. Okay, here we go. That's a theorem here. Take a look here. Oh, this last line here. So it was property 1. Okay. Here we go. This line right with that. Okay, why the screen becomes stuck? Okay. All right. And let me just end this talk by comparing them with this paper by John 2020. I don't know why it does not show up, but Charles Gao's paper. He's at the University of Chicago, and his student, I believe. So in that paper, instead like us, we get a variation posterior individual model, and then we aggregate them. In their model, they only pick one best model. Okay, so that's basically what this notation here. They pick this. Find this M, the particular model that minimize this object function. Okay. So unlike ours, we do sort of aggregation of individual variation approximation. They try to find the best individual model that provides the best approximation. We're going to show you that our framework is going to be better than theirs in several perspectives. The first one is from the responder perspective. Okay, we're going to say their variation posterior, we call it the model selection variation posterior, is suboptimal in approximating the regular posterior distribution. Okay, so here first you see that. So the KL first in this proposition shows that the KL divergence between our model and the true regular posterior distribution is bounded above by the KL divergence of Charles Gao's variation of posterior to the regular posterior distribution. This is in terms of KL divergence. Okay, and this theorem will give us the risk bound here. The risk bound is is going to be this is the Oracle risk bound. I'm going to show basically our risk is always smaller than his risk of his variation posterior distribution. Okay, I'm almost done. And the other one will be, but if his model can choose the track model, then we will show the two of them are equivalent. Okay, our variation posterior distribution, and here's the equivalent. Okay, and conceptual comparison, as I brought it up, there's this notion of Bayesian model averaging versus the Bayesian model selection. Okay, in general, I was more flexible and more robust model specification. And from model selection point of view, you can think our adaptive variation posterior distribution as a soft decision making, right? We are weighting our models lining sort of with weights lining between 0 and 1. But in that case, they only pick one particular individual model. Okay, so we would say our adaptive variation in Bayes is more flexible as a soft decision versus the harder one. Okay, and I will show you. I will show you the end of my talk with one last picture. So the data generated from a four component mixture. Okay, so and if you take a look at the Charles Gao's paper will be here, M equals 3, because gamma had a 3 point equals the variation of posterior probability equals 0.57. So that model is this one, M equals 3. So it looks like they select 3 components. There's only one volley here, right? One sort of one class here. But ours, the last panel here, the AVB aggregates everybody, right? Then we get the better results. You can still see like 4 cluster, 1, 2, 3, 4, right? Although the separation, of course, not as good as the true model, but still, I think we were able to identify like sort of a 1, 2, 3, 4. So you can at least see 4 class, small class, 4 class here, 2 class on this side. Why in Charles Gao's paper, MSVB, those 2 classes almost stick together? Because because they basically choose that the inference basically yields a model with 3 clusters, why the true cluster is 4. You know what I mean? Because they have to pick one single model that works best for that. Okay, so, and I know I only cited his work, John and Chagao, and our work, which is coming up soon. So when I post the paper on archive, and I'll probably share with Katie, and if she can share with it or everybody, that would be great. So when I was preparing the abstract, I thought my people would have been done by now, but it's not up in archive yet. But it will be up maybe a couple of weeks, hopefully. So I have draft here. I'm getting down to 60 pages. Hopefully, we can finish up the proof, and then I'll post on archive and share with everybody. Okay, so sorry I'm be talking the whole hour, but anyway, so if you have questions now, or if you have questions later, if someone happens to watch the video, if you have interest in this adaptive variation posterior framework, you can always reach out to me, or you can ask Katie for my email.
Well, thanks so much, Lizhen. This was a really interesting talk. I like the idea of the flexibility, the scalability, and also the idea that it could be eventually applied to neural network architecture decisions. That sounds really cool, and it's a big open question that a lot of people are sort of fighting with. And we are up against time, so I know we're going to lose a lot of people, but there is one question in the chat, and I will read it for you. Hello, Professor Lin. Thank you for the amazing presentation. Is it possible to find these slides on Google Scholar? Okay, well, we are definitely going to put these up. And I'm not sure if this is a trivial question, but for optimization, is there a specific method like the simplex algorithm or something like Lagrange multipliers or the Newton method? So what is it that you're using for optimization?
Okay, that's a great question, but I'm really not expert in computation. I have the project, but my postdoc actually is. So I would say the one thing I want to comment on is our framework, adaptive variation framework, does not impose new computational thing, right? So whatever algorithm you can use for individual model, or you have to just aggregate them for our framework. But in terms of specific, what's the best algorithm for variational Bayes, I'm not sure because I haven't really implemented one myself. But if you don't mind, like reaching out to me a little later, like by email or something, I can check with Ishan for example, what he did for this particular model. Like I said, I think he's also trying something for the deep neural network model. At least for that one, I think it's very important to know what he's using, I would say. But in general, the variation computation is very popular. So I think if you read Dave Blind's like review paper or something, that some of them would definitely you can just use one you can use one, those algorithms that he suggested in his review. So.
And I guess I'll wrap up with one last question from me. So this is a very general variational Bayes question. So since you're kind of trying to make assumptions about the form of the posterior, what that made a connection for to me is choosing conjugate priors. So how does variational Bayes compare to that? Does it end up being more flexible and more accurate as opposed to kind of choosing a prior that makes sense with your likelihood, or do they kind of perform the same?
Yeah, okay, that's such a good question. But a lot of time you don't have the simple thing of conjugate family, you know what I mean? So if you do have a simple model, right, you can have like relatively simple model, you can have a conjugate prior, get this nice form of posterior distribution. I would say definitely I would like to go with the 4 Bayes methods, right? Then you get this 4 posterior distribution, the regular posterior distribution. Because no matter what, if you provide approximation, a variation, especially if you choose a variation class that's not in the same conjugate class, you know what I mean? So the approximation, the average is going to be worse because it's an approximation. You know what I mean? There's always this K of divergence is not going to be 0. You know what I mean? So there's always a divergence between the two. So to answer your question, if the closed form solution like a conjugate prior for the models available, I will go with that. And on the other hand, the variation of Bayes is more flexible, right? Even if you don't have a conjugate prior, I can have a simpler class of variational model that a variation family that can provide approximation to potentially pretty complicated posterior distributions.
That's a really good point, because a lot of times choosing a conjugate prior doesn't actually make sense for your prior information. So there's some flexibility there.
Yeah, exactly.
Well, since we are a little bit over time, I will go ahead and wrap things up here. Thanks, Lizhen, for your great presentation, and thanks everyone for coming, and thanks to the audience who will see this in the future recorded, and I will see everyone at the next seminar.
All right, thank you. Thank you for coming to my talk. I'm sorry I've been talking all the time. I wasn't sure whether I should have stopped more for you for more questions, but I just had so many slides. But anyway, okay, it was nice meeting you all. Thank you. Thank you, Kitty. I'll reach out to you later about some,
Sounds great. And anyone feel free to follow up with our speaker if you have any more questions and would like to know more about her work.
Okay, bye. Thank you.
Bye, everyone.